These videos are going to talk about the proof of why Lagrange multipliers work in a very general setting where we have multiple constraints and where we have the technology of the matrix of derivatives and the implicit function theorem and a knowledge of some of the linear algebra that goes along with that. So I don't want to start out just loading up with the definition and the statement of the theorem, even though that's where we're going to head to. The first thing is just to look at a specific example. I've got a function, and I'm going to write that example out in what's an unnecessarily complicated way for this example, but will be an example of how we write it out in general where it really is necessary. So here's a function on R3, pretty simple linear function, and its matrix of derivatives at any x, y, z, well, it happens to be constant, doesn't actually happen to depend. It's a 1/3 matrix, and we're going to call that capital F in this situation, just to have a very simple notation for it. Not a standard notation, but okay. The gradient of F at x, y, z then is just the transpose of that. Really, for deeper purposes, it's really important to realize it's a row vector, but a lot of the time there's no harm in taking its transpose and thinking of it as a column vector, and that's where we get the idea of the gradient as a vector field. Okay, so what do we want to do? We want to find the maximum and minimum of that. We want to really find all constrained extrema, and maybe just even all constrained critical points of this function on the level set of some other function. So, one of the things about Lagrange is the basic idea. Well, let me write it down here. Let's say it's the sphere, and I'm going to cheat a little bit to make the numbers come out really nice. It's the sphere radius 14, radius root 14. So we've got this picture, we've got a set, that's a sphere, and then we've got this linear function that gets bigger as you come toward us in the first octant and gets smaller and negative as you go away in the opposite octant where all the x, y, z are negative. And we want to find where that's biggest and smallest. If it has some saddle points, those might be interesting, and this method is going to find those anyway, even if we don't want them. And the one thing that's important about Lagrange, that hopefully if you have seen sort of a basic treatment of Lagrange it's important, is that there's a more general problem you could ask. You could look at any set whatsoever, or even any relatively nice smooth set, and look for where are the constrained extrema or constrained critical points on that set. That's not what Lagrange applies to. Lagrange applies to the case where that set is the level set of a nice function, a smooth function, differentiable, with even another nice property that we're going to discover what has to be true about it. Luckily, that's very, very often how we define interesting sets, is level sets of nice functions. Okay, so that's where this is going to apply. And it's going to apply a bit more generally when we get to the more general case, but that's the basic case. Okay, so let's look at the derivative of this guy. Okay, it turns out to be crucial to look at the derivative of this guy. This guy does depend on where we are in x, y, and z. Okay, that's 2x, 2y, 2z. And crucial thing is that on this set, if not at the origin, which is clearly not in this set of radius root 14, this is not the zero vector. Or really, what's important, if we call this matrix G as a transformation, it's onto, or it has full rank, is another way to say it. The rank, what's the maximum rank a 1/3 matrix can have? Rank of G is equal to 1. Okay, so we'll see why that's interesting in a sec. Well, we'll see right now, really. Here's where some pretty big machinery comes in. The sphere is obviously, because we're so familiar with it, it's obviously this nice, smooth, wonderful set that every point on it has a nice tangent plane. It's nice and smooth. It doesn't have any corners, cusps, anything like that. But how do we know that in general? Well, that's the big theorem that's underlying all this, the implicit function theorem. What does the implicit function theorem say? It says that since dg, that is our matrix G, is onto, as big a rank as it can have. It says that this set where g equals 14, no root, is nice. Well, what does it mean, nice? It really means we can transfer from one description as a level set to another one of the very useful descriptions as a parameterization. So this is a set of possible inputs, x, y, z, that have a certain fixed output, and a parameterization is the set of all possible outputs of a map that goes into R3. So what it says is that there is excuse me, there is a map, there's a smooth map, and smooth in different variations of the inverse function theorem can mean slightly different things. Here it means C1, although we probably want C2 at least for if you want to start doing second derivative tests and things like that. That's not the important part here. Let's call it phi. Okay, well, what is this? This is a two-dimensional surface. Actually, let's just bring the picture back a little bigger. And what the implicit function theorem says is that you should be able to pick some pair of the variables, either x and y, or x and z, or y and z, and use those to parameterize the point. Now, it doesn't guarantee, it doesn't say which one of those you're going to be able to use, and it doesn't say you can use the same pair for all points. So, for example, the upper hemisphere, if you don't use the equator and you just use this top, then that can be parameterized as a graph of a function of x and y. But that does lose you the equator, because there the derivative goes vertical of that map, and you can't do both upper and lower simultaneously and be a single valued function. Okay, so we really one of the subtleties here is that I can't say absolutely for sure right now which two variables are going to work, except I happen to know kind of where this is actually going to end up being interesting, where the constraint critical points are going to be, and I happen to know that x and y work. So let's see. Let's put it here. Phi of x, y is, and what is it? It's just the z. It's just you solve for z. Root 14 minus x squared minus y squared. In this case, it's totally easy to actually find that explicitly. The power of this whole method here is that by analyzing these specific cases and then generalizing, we'll see that without ever being able to do this explicitly, or even trying to do this, just knowing that in principle it exists, we can actually develop things like Lagrange multipliers. Okay, so another way to say this is there's a parameterization. So it's going to be the graph of this function. Okay, just saying z equals that is another way to describe at least a fairly large portion of this sphere. Okay, excuse me. I'll try not to make this one of my coughing fit videos. Another way to say it, a little fancier, is there's a parameterization. Let's say capital phi, and let's say just phi of xy is, and it leaves x and y alone, and then puts in this guy at the end. Okay, so that is the situation where we've got x and y separated out into essentially another little mini universe here, and phi, as all good parameterization maps are, is a one-to-one map from this domain producing a point on the upper hemisphere. Okay, so it's going to turn out to be interesting, of course, to analyze the derivative of that map. Does that have nice properties? Well, phi is not just a one-to-one map. To be a parameterization, to be a good smooth parameterization, d phi should be one-to-one. Okay, if I'm wiggling a little bit here, that should be faithfully recorded as some sort of wiggling here, and that's what guarantees that I have some sort of nice tangent plane here. Okay, and indeed, of course, it's pretty easy in this explicit example to calculate d phi. It's 1, 0, 0, 1, and then it's not too hard to figure out the derivative of this guy. It'll be a little exercise for you. Partial derivative with respect to x and y. Remember, z, I'm just going to think of z as a shorthand for this expression, and then it turns out to be minus x over z minus y over z. Okay, I'm just lazy to write that. Okay, of course it's a meaningful shorthand because that is the z coordinate in 3 dimensions. Okay, so let's call that A, just so I don't have to write as many letters when we get to the crucial algebra. Okay, and what's the key? So now we've got the setup. Okay, there's an intimate relationship between G. This is where we started to find. This is the implicit definition of the sphere. And phi, that's the parameterized definition of the sphere. Okay? The whole point was that phi creates points on the sphere, but what's supposed to be special about points on the sphere? It's that G of an explicitly created point on the sphere is supposed to be 14. And that's constant. The whole point was that it's a level set. Okay? Or in other words, G composed with phi for all of its arguments is a constant. Now, what does that say about the derivatives? It says, by the chain rule, dg of some x, y, z that's actually on the sphere, composed with, that's a matrix. It's really a row vector, but it's, the kind of matrix. Composed with d phi of the xy that it came from. These, of course, have to match. The xy have to match. Well, that's the derivative of a constant. That's 0. Okay. Or in other words, just kind of ignoring the point of evaluation stuff, because that's not something that's really going to get screwed up here. It says that the matrix G times the matrix A is the 0 matrix. That's slick. That's very elegant. Okay. So, excuse me. Alrighty. So, let's check that. Okay. Let's not trust it too much, because we have these matrices written out, right? We know that dg is 2x, 2y, 2z. You know what? I need enough space to multiply them together. Okay, so dg is 2x, 2y, 2z. And then here's d phi. And indeed, if you look at the dot product, if you turn that into a column vector, notice how that's taking the transpose of this guy, and that's going to come in, and dot it with this. You don't have to think about it that way, but it's pretty traditional too. You get 2x minus, the z's cancel at 2x. Okay. And you get 0. And then row by column again, you get 0. So indeed, that's the 0 matrix. But that's not something we actually had to check, because it's guaranteed by the chain rule. Okay, so now that's the relationship between little g and phi and the matrices big G and A, their derivatives. Well, now what do we want? Remember, f hasn't come into this at all yet. We want a local max or min, or we might accidentally find a saddle point or something. Local, critical point really, of this matrix, this function f of x, y, z is x plus 2y plus 3z. Now, usually that's going to be something that's really hard to do in any other way, or else we wouldn't be using a fancy technique. But let's go back to the picture. In this case, I claim we actually know what it is. Okay, x plus 2y plus 3z. What are the level sets of this guy? They're planes with normal vector equals 1, 2, 3. Okay, so they're planes that are coming out toward us into the first octant, where everything's positive, going down into the other octant, and their normal vectors are 1, 2, 3. Well, the place we're going to get a local max of that function is exactly where the last plane, as you come from the ones that are away from us and moving toward us, where that last plane is just touching, and of course its normal vector is perpendicular to the plane, but the plane is tangent to the sphere, and we know that that's perpendicular to the radial vector. Okay, so guess what? It should be this point x, y, z should be some multiple of 1, 2, 3, and this is why I chose 14. This guy has x squared plus y squared plus z squared equals 14. Okay, so in this one we actually can guess the answer. I wanted to pick that so that we can be just really sure that this is the right answer, and then double check that the fancy schmancy method is actually giving that. Okay, so let's look at this. Okay, so at that point, so this is a little fake because I know the answer all ahead of time, but you don't start out with the hardest problem. At 1, 2, 3, okay, what is the G matrix? It's just 2 overall factor times 1, 2, 3 as a row vector. A, let's write it out. It's always this stuff. And minus 1/3 minus 2/3. And of course we checked that this matrix times this guy is 0. Okay. Now what do we need? We need what should be true about the relationship of little f, that function, and all this story? Well, it's a relationship about the derivatives. Okay, I claim that if I let f, as I had before, be the derivative of little f, oh, that's 1, 2, 3. I claim that it's not an accident it's not accidental that in fact f times a times this matrix, of course that's equal to 0 as well, the 0 matrix as well. Why is that happening? Why is that also the 0 matrix? Well, it's not just because I set up the example in a contrived way. We know that f composed with phi, let's look at that, f composed with phi of xy. I'm going to have to draw the parameterization map again. Here's phi generating, big phi, generating points on the sphere in some little region there. And what's supposed to be true? If I look at some xy, and now this is going to be, let's say x naught, y naught. Okay, this is the 1, 2 in this case. This is the point that we already kind of cheated and we know is a critical point. In general, we're not going to be able to cheat and just know that in advance. 1, 2. I know that if I wiggle that way, that wiggles on this sphere, and I only get lower. It's in all the directions because I'm going away from that magic point where that last tangent plane hit, where that last level set of f hit. Okay, so this guy is a critical point of this function. I think of the function, the composed function, that takes a point in the parameter space, creates a point in actual physical space where I'm interested in, then evaluates the function. The highest I'm ever going to get is right here where I'm already sitting. That means I'm at a local max of this function, this ordinary function of two variables, no constraints. That's what the parameterization allows us to do, is to consider this function where the constraint has been just kind of hidden. And this guy has a local extremum, and therefore it's not because it's always constant, but because it has a local extremum. That's 0, but that's df at xyz composed with d phi, very much like with the G story. Or in other words, fa is also equal to 0. Okay, so that's why this guy was also equaling 0. Now, in this case, it's pretty simple. These guys are just scalar multiples of each other. So of course they're going to behave very similarly. And really, and the key of the logic here, this is getting a little long, but we're almost done with this example. The key of the logic is that this is really what we'll always know. We won't necessarily know exactly what f is. That's a bit of a mystery. But we know it's some mystery row vector that when you multiply it by a, you have to get the 0 matrix by this calculation. But wait a minute, we've seen this before, okay? So we've got, let me turn it upside down. We've got fa equals 0, but we also know that ga equals 0. And that means there's going to be some very nice relationship between the matrix of derivatives of f and the matrix of derivatives of g. What is the relationship? Well, here, let's look at the dimensions. This is a 3 by 2 matrix. These are two vectors in three-dimensional space, and they're not collinear. If they're collinear, this matrix would not be 1-to-1. It would not be a good parameterizing matrix. Okay? And so how many vectors are perpendicular to two non-collinear vectors? There's only one dimension's worth of vectors. It has to be a scalar multiple of these guys. Okay? So I've got these two matrices, these two 1 by 3 matrices, f and g, that both kill a. that, in other words, when I think of like the transpose, another way to think about it is F transpose, that's the gradient of F, and G transpose is the gradient of G. These guys are both perpendicular to both columns of A. That means that they have to be scalar multiples of each other. So in other words, F is a scalar multiple, let's call it lambda, of G, or the gradient of F is a scalar multiple of the gradient of G. And that's the key to why Lagrange multipliers work, that these guys must be in the same direction. Now, there's definitely simpler ways to see this in this kind of case, focusing more on the geometry and the arrows and the level sets and things like that. But it's really going to come back to these three matrices in general. The A matrix, which is d phi, coming from their parameterization. The G coming from the level set or intersection of level sets. That's where it gets more complicated. And F being the derivative of the function you're trying to extremise. All right, that was long enough.